When it comes to the analysis of forces, there's a few different types of situations you might experience. I'm going to attempt to show you a method that will apply to all of them. You just have to make sure your concepts are in order. We'll look at three different situations. Two examples where you have zero acceleration, one example where you have acceleration, and the last example will include a force that's at an angle, and I'm going to attempt to show you how the method that, not necessarily that I recommend, but the method that I'm going to show you is a nice, easy, organized way to apply, that applies to every one of these situations. Now, the main thing we need to realize, as we covered recently, is that the net force is that total force that acts on an object, and there's two ways to find that. We can add up the individual forces, force of tension plus force of friction, etc., depending on the forces you have. But also, Newton's second law claims that the net force, the total force acting on an object, will cause that mass to accelerate. If you can remember that these are two different methods to find the net force, it's equating these two, setting them equal to one another, that's going to help you to solve for quite a variety of forces and therefore analyze quite a variety of situations. I think the easiest way, it's going to be hard to just explain this conceptually, so let's just go through the examples and I'll kind of add in concepts as need be. So if we look at the first example, it's fairly straightforward. We have a person pushing a box. The box has a mass of 20 kilograms. If that applied force is 30 newtons and the box does not move, well, let's see what it looks like to draw the free body diagram. And then more importantly, that next step would be calculating the normal force in this example and also the force of friction. So we're going to combine our free body diagram concepts with Newton's second law, and hopefully we're able to start determining specific forces, which is exactly what they would do in the real world when they design buildings, cars, engines. Anytime they need a force, you're basically going to use Newton's second law, among other things, but Newton's second law is very helpful. So if you look at the free body diagram, you can ignore this chart on the side for right now. If we look at the free body diagram, well, we certainly have gravity acting down. We have the normal force from the floor acting up because that's two flat surfaces pushing against one another. We have the applied force from the person, and we also have the force of friction because the box and the floor are not sliding, so there must be some force that's counteracting this applied force. The next step would be to ask which of these forces are known. Well, the 30 newtons was given to us in the problem. And the force of gravity, if you remember, is just mass times acceleration. And since it's gravity, it's the acceleration due to gravity. So 20 times 9.81 is 196.2 newtons. Now, once you've done that, this table method is not necessarily required for a situation like this where you don't have any movement or acceleration with the object. But I'm going to show you why it might be a good idea to just organize all of your forces. What we've basically done is drawn two columns, an x and a y, to account for my x forces and my y forces. So all I've done is I've said, well, I have a 30 newton force to the right. I'm going to assume for my problem that to the right is positive. So I have plus 30 newtons. That's my applied force. The force of friction I don't know, but I do know since it's going to the left, it must be negative. So I have a positive 30 newton force to the right. That comes from the person. And I have the force of friction acting in the opposite direction. Remember, in physics, positive and negative just means opposite. I do the same for the y. I assume my normal force, which I don't know right now, is positive because I'm going to assume positive is up. I'm going to assume negative is down. Therefore, my force of gravity is really negative 196.2 newtons. Then all I do is I just sum them up. The total of my forces up here is positive 30 minus the force of friction. And in my y direction, it's the positive normal force minus the force of gravity. It might be hard to realize right here, but all I've done by setting up this table is calculate the sum of my forces in each direction. F1 plus F2 plus F3, etc. in the x, and F1 plus F2 plus F3, etc. in the y. So that's all these equations are. You didn't have to necessarily draw a table. You could have also said, well, 30 newtons to the right, force of friction to the left, and you could have just derived 30 minus force of friction by yourself. Same for the y force. But this is a nice way to keep it organized, and it will help when we start to do things like forces at an angle. But just understand that this method right now will work. The next step would be to find those individual forces, the normal force and the force of friction. So if you take a look, the question you should always ask yourself, is the object accelerating? Well, if you look up top, the box does not move at all. That means it's not moving or accelerating in the x direction. It's also not accelerating up or down. So the acceleration in both directions, the x and the y, is 0. So all I'll do is basically plug all my numbers into this equation up here. And we have my net force in the x is going to equal my x forces, the sum of the x forces, my 30 Newton applied force minus my force of friction, and that's also going to equal mass times acceleration. And I'm just going to say mass times acceleration in the x. So 30 minus the force of friction equals the mass, which is 20, taken from the problem, times the acceleration in the x, which is 0. So 30 minus the force of friction is 0. My force of friction must be 30 newtons to the left. I'll do the same thing for the y, but I realize since it's not accelerating up or down, that my net force in the y, which is this equation taken from up here, must be equal to the mass times the acceleration in the y, which again is 0. So the normal force minus 196.2 equals 0. Therefore, the normal force must just be 196.2. Again, you didn't necessarily need to do this XY table, but it's a nice, clean, organized way of making sure you've accounted for all your forces. So that's more of a straightforward problem. There's a second example where we can have zero acceleration, and that's cases where something's sliding at a constant velocity. And I find that trips up students the most. They see constant velocity, they realize it's moving, and they start to get confused. You just have to realize constant velocity means there is still zero acceleration. There's no difference in analyzing this problem than there was in the previous example. So in this case, we have a 20 kilogram mass box. It's moving at a constant 5 meters per second. And let's take a look at how to draw the free body diagram. And then in this case, I would ask for the calculation of the normal force. So here I've drawn my free body diagram. We have gravity acting down, normal force acting up, and there are no other forces. There's nothing pushing this block forward. If you were wondering whether there should be friction, well, if there's nothing pushing it forward, there couldn't be friction pulling it back. If there was friction pulling it back, you'd have more force in one direction. This object would not slide at a constant velocity. It would actually slow down in that case. So we'd have to assume that there's no friction. So again, I've just drawn my XY table. We have no X forces. There's nothing pushing it forward. And we've determined there can't be friction because otherwise the box would slow down. So there are no X forces. In the y direction, the normal force goes up. It's unknown, so positive Fn. And the gravity is just, again, the mass times the acceleration due to gravity, which is 196.2, and that's negative because it acts down. So I'll just sum up my forces again, and I know that the net force in the y direction is going to be my normal force up minus my force of gravity down, and that equals the mass times the acceleration in the y. Now we know that this box is sliding at a constant velocity to the right. It is not accelerating up or down, so my acceleration is 0. So therefore, Fn minus 196.2, the normal force minus the weight of gravity, must equal 0. And therefore, the normal force in this case must be 196.2 newtons acting up. That's the force of the floor on that crate. Again, same method. It's just a nice, clean way of keeping your forces organized. The third example, well, now we have a situation where the object is actually accelerating, and I'm going to attempt to show you how this method is exactly the same, just with slightly different values. So here we have a 20 kilogram mass. It's being pushed by a person with an applied force of 50 newtons to the right, and the force of friction, in this case we do have friction, it's acting to the left at 30 newtons. So again, we'll look at how to draw the free body diagram, find the normal force, and then determine the acceleration of the box. Slightly different problem, same exact method. So if we look at our free body diagram, I'll hop back and I'll leave like this. So the applied force acts to the right, friction acts to the left. That was given in the problem. Hopefully by now you realize the force of gravity acts down towards the center of the Earth, and the normal force acts up. So all I've done is plugged in what I know. I know that 50 newtons is my applied force, 30 newtons is my frictional force, and I've calculated the force of gravity using mass times 9.81, which gives me 196.2 newtons. Then all I've done is I've set up my XY chart again. In the X direction, I have positive 50 newtons to the right, that's the applied force. I have negative 30 newtons to the left, that's the force of friction. In the Y direction, I have the normal force acting up. Positive, I have the force of gravity acting down. All I've done is sum my forces. Again, that's just like F1 plus F2 plus F3, etc. And summed my forces in the Y direction. Now I have to ask myself again, is the block accelerating? Well, we know it doesn't accelerate in the Y direction because this block is accelerating this way. There's nothing pushing it up or down with more force. in one direction, so therefore it's not going to accelerate up or down. It's the same reason why when you push like a chair or a desk across the classroom, it doesn't accelerate towards the ceiling or accelerate towards the floor. It will accelerate in the x, but not in the y. So there is no y acceleration, so that's 0. There is an imbalance of forces here. I have more force in one direction than the other. Therefore, there is an x acceleration. I just don't know what it is just yet. So first, let's look at my y forces. Well, the net force in the y is going to be my total sum of forces, Fn minus 196.2, normal force minus gravity, and that's going to equal mass times acceleration in the y, which is 20 times 0. There is no y acceleration. So the normal force minus the force of gravity is going to equal m times a. Because a is 0, it will equal 0. If I rearrange this equation, the normal force simply equals 196.2 newtons up. I can do the same for the x. We know my total force, the sum of the forces in the x is simply 20. And we know that that's going to equal mass times the acceleration. We don't know acceleration here, but we do know mass. So when I plug in 20 kilograms times the unknown acceleration, I wind up with my net force of 20 equals the mass, which is 20, times acceleration in the x. Therefore, this object accelerates at 1 meter per second squared in the x direction. So as you can see, the method is exactly the same. It just matters at the very end which specific variable you're solving for. But this method will work for every single situation we've described so far. The last one is probably the most difficult, but again, I'm going to show you how this method can be utilized. So here we have a 5 kilogram block. It's being pushed to the right by some kind of compressed spring. Excuse me. We have an applied force of 10 newtons that acts to the right, but also upwards. So it actually acts at a 30-degree angle. And we're given that the block accelerates at 5 meters per second squared to the right. We're going to assume that, I apologize, this is incorrect. We are going to assume there's friction. I believe I'll give you that value in a second. So I apologize for this. This is incorrect. Please do not write this. We would like to find the spring force. We'd also like to find the normal force. And again, I'll give you a value for friction. I do believe you need that. But before we do that, let's look at this concept review. If we think all the way back to the beginning of the year, we would look at situations where you'd have some kind of velocity at an angle. And we would find those x and y components by using cosine and sine, because we could set up a right triangle, and cosine is used to find the x, and sine is used to find the y. So hopefully you remember that. The good news is that force is also a vector, so the x and y components can be found using the same exact method. If you know some force at some angle, like in this situation here, we can use this force, 10 newtons, times sine or cosine of this angle in order to get my x or my y. It's no different. That's a concept we can apply to every type of vector. So with that in mind, let's look at this problem. I've drawn my free body diagram. We have gravity and normal force up. The spring force pushes to the right. The force of friction resists that. And then we have our applied force, which I've changed to 20 for some reason, because this problem is a big mess. So I'm going to use 20 from this point. So I apologize. This problem is riddled with errors. But we're going to assume that this is 20. It acts at 30 degrees, and everything else is as you see that. So spring pushes to the right, friction resists, gravity pulls down, normal force from the floor pushes up, and there's an applied force of 20 newtons, let's say, that acts at a 30-degree angle. So what we're going to do now is, after I've calculated everything, I know this is 20. I know that my force of gravity is 49.05. I do believe that the force of friction in this case, I assume this was 5 newtons. I don't have this written anywhere, but please make a note that I have the force of friction being 5 newtons. I've drawn my XY table, and it's no different than before. I have the spring force, which is unknown, acting to the right. Again, my force of friction I've said is 5 newtons, so that acts to the left. The only thing that's left is, of this 20 newtons, some of this is pulling to the right, and some of it is pulling up. If I want the section or the portion that pulls to the right, the x portion, well, I just have to use that force times the cosine of the angle, which will give me the x component. So my force is 20, my angle is 30. So 20 times the cosine of 30 degrees will give me the x component of that force. I'll do the same for the y. I have the normal force acting up. I have the force of weight pulling down, or the force of gravity. And if I want the y component of this force, again, I just have to use the sine of that angle. So 20 times the sine of 30 will give me the y component. So these two forces here are the applied force. It's just the portion of the applied force that pulls to the right and the portion of the y force, the applied force that pulls up. All I have to do again is sum these up, and I get the spring force minus the 5 newtons of friction plus the x component of the applied force, and over here the normal force minus the force of gravity plus the y component of the applied force. Then I ask myself, what are the accelerations? Well, we're given the object accelerates 5 meters per second squared to the right. If you've ever pulled a block, you realize that unless you're pulling straight up or with a large amount of force, it's not actually accelerating up or down off the table, so therefore the y acceleration is 0. So once I have these net force equations and I have my accelerations, it's as simple as just setting your net force equation equal to your mass times your acceleration. The mass in both cases is 5, the difference here being in the x I have an acceleration of 5, in the y I have an acceleration of 0, and if I go through and solve these out, I will get the spring force, which is the only unknown force in the x, is 12.68 newtons to the right, and my normal force must be 39.05 newtons directed upward. So that was 4 different examples. I recommend you use each one as you need them. You can always come back and watch this video, but just realize that the method for each is the same. Draw your free body diagram, figure out what forces act in the x and the y, find your net force equation, and then once you analyze the accelerations in both directions, it's just a matter of doing your algebra right.